Hey everyone, Professor Davis here again to talk to you a little bit about hyperconjugation, specifically how that applies to carbocation stability. So carbocations are most stable when they're more substituted. We know this from our lecture course. And we also know that alkyl groups are weakly electron donating, and that's the mechanism by which they stabilize carbocations. Because reducing or delocalizing charges in small organics gives those ions greater stability. So we expect methyl carbocations to be very rare because they're so unstable. Primary is not much better. But when we get on to secondary and tertiary carbocations, we see these constantly in organic chemistry. These are staples of first-order substitution and elimination reactions. And the reason is that those alkyl groups are increasing the stability of the carbocation. So let's take a look at what it is about these R groups that allows them to donate electrons or to put electrons close to that carbocation center. So here I've drawn for you the methyl cation and the ethyl cation. And these two carbocations you're not really going to see in a genuine bona fide reaction because they're just not stable enough. But they're the simplest examples that will allow me to demonstrate how hyperconjugation works. So let's set aside the fact that these are unreasonably unstable and just take a look at them right now anyway. So I'm going to turn them into three-dimensional representations, and then I'm going to turn these representations on their side. And when I do this, I can place the unoccupied p orbital of each carbocation center vertically in the plane of our page. Now, what's different between the ethyl and the methyl cations is that the ethyl cation has a neighboring CH sigma bonding molecular orbital. And this bonding molecular orbital is actually filled with electrons. That's how it's holding on to the hydrogen. But we also know that these electrons, though I've drawn them here in between the two bonded atoms, we know that they actually have free run of that entire volume that is defined by the molecular orbital. So they can run all around, up and down. And as you notice, occasionally they find their way over to the empty p orbital on the carbocation. And when this happens, they slightly attenuate the positive charge, thereby decreasing it. And remember what we said previously. Anything that decreases or delocalizes charge in small organic molecules or ions is going to stabilize them. So this is why having additional alkyl groups around a carbocation center makes them more stable and therefore more likely to form. So next time we'll talk a little bit about how this hyperconjugation and the stabilizing effect of alkyl groups on carbocations leads to things like hydride and methyl shifts. And I'll see you then.